Okay, everybody, today we are going to be looking at the law of conservation of matter and how we can use this law to interpret balanced equations. Okay, first and foremost, what the law of conservation of matter states is that matter cannot be created or destroyed in any kind of change, whether it is chemical or physical. A lot of times we only think about the chemical changes when we talk about this law, but if you think about it this way, if you rip a piece of paper in half, which is a physical change, the mass will still be the same. It's just the paper is now in multiple pieces. So the same law applies to any kind of change, whether it's chemical or physical. All right, so one classic example is rust, and we can use rust to prove the law of conservation of matter to be true. So you leave your bike out for too long outside, the oxygen can cause the metal on your bike to rust. So this is a chemical equation. And what it's telling us is that there's a certain amount of atoms in matter. Now, this arrow always represents a change, all right? And the change has created something new, a new substance. So rather than use the word create, you want to use the word form. So the change has formed a new substance. Sometimes you'll see things like heat or light that'll also be given off as well in a chemical change. Now, we started off with a certain amount of matter on this side, and we are going to end up with the same amount of matter on this side. This is what it looks like on a molecular level. There's 4 atoms of iron. There's then 6 atoms of oxygen, all right? 3 molecules of 2. Once that change occurs, all right, the properties of the metal cause these atoms to rearrange. So if you notice, there's still the same amount at the end result of the equation. However, they're just in a different pattern. This is the piece where we say we can't create or destroy. They've formed a new substance because they have rearranged, so their composition has changed. Excuse my family text message at the corner. All right. Now, you're going to see open and closed systems mentioned when we talk about the law of conservation of matter. This is a closed system because this glass container is keeping all of the matter contained in this system. So we started with 100 grams of coal. We ended with 100 grams of gas. So you can think about our Alka-Seltzer lab with the gas bubbling. The mass was about the same in the beginning and end of the lab. Gas still accounts for mass. Now, an open system, if you were to take, say, a lid off your boiling water, this would be considered an open system because the matter can escape into the environment. So you might technically have less mass, but it's not like it just went away and went nowhere. It just escaped in the open system. So why don't you take a second to pause here and think if you can think of some examples of open and closed systems and how they prove the law of conservation of matter. Okay, so if you've pressed play again, some classic ones I think of for open systems are logs burning on a fire. You know, the mass escapes into the atmosphere. I also think about boiling water. I also think about in the chemistry lab if we are boiling cylinders on a hot plate with no container. Closed systems would be adding those containers, a sealed bag, a vacuum, or even a tied up sealed balloon. Okay, now balanced equations are another model that can prove the law of conservation of matter. In every equation, there's reactants and there's products. This is going to help you with your homework that's due on Friday. So the reactants, we say they race in, or in other words, this is what's being combined, something's starting here. Then the change occurs, which is signified by the arrow, and we have the end result of the products. What this diagram shows you is that each number is the same on the reactant side as the product side. So there's 3 carbon atoms, 8 hydrogen, 10 oxygen. But if you look from one side to the next, you'll notice that the numbers have kind of rearranged themselves. So let's take a look at this step further. If the number of atoms of each element are the same on the reactant and product side, it is called a balanced equation. So what you do is you use the distribution method to kind of figure out if you have a balanced equation or not. So looking here, the larger number in front of an element is a coefficient. It gets applied to every element behind it. You can kind of think of the plus sign as like where it stops, separates, so it doesn't go into here. So there's 2 hydrogens. Now there's also a subscript behind it. When there is a subscript and a coefficient, you multiply them to get 4 hydrogens. Product side, this 2 is going to get distributed to this H and to this O. Then you will multiply this subscript only to the H. So this matches up, where we have 4 hydrogens, 2 oxygens. Let's look at this example. 2 sodiums. There is no coefficient here at all. There's no subscript behind this C. So this C only accounts for 1 carbon atom. 3 oxygens. Okay, now let's distribute this 2. 2 hydrogens, 2 chlorines. All right, so we're looking for the other side, 2 sodiums. That's the case. We're also looking for 2 chlorines, also the case. All right, let's check our hydrogens. 2 matches up here, 2 as well. Now, say I have 1 oxygen atom in one compound, but I have another set of oxygen atoms in another compound. I add those together. So since I have 1 here, there's no coefficient, there's no subscript, I have 1 oxygen atom in this compound, and I have 2 here. When I add them up, I get 3. So that checks out. Last, I should have 1 carbon atom, which is true because there is no coefficient in the front and no subscript behind. Try your best to practice with the next 2 examples, and you can have me check them when you're done. The packet that is due on Friday is going to continue to practice acknowledging balanced equations so that you can be prepared for the quiz on Friday. Thanks, everybody.